Alright, so today I'm going to be talking about the photoelectric effect. I'm going to be talking about the formulas and the equations used. I'm also going to be talking about wavelength and how that all equates to each other and kind of the conceptual aspect of wavelengths in chemistry. I kind of want to highlight the fact that light is composed of waves and particles. So it was once thought that light was only composed of waves and not so much particles or not particles at all. But it was then proved by the photoelectric effect that light actually has photons and they can act like particles and can actually knock electrons out of a metal surface if the frequency is high enough. And so let's understand what that all means, right? So let's talk about the fact that, or let's just go over what a wavelength is, right? So a wavelength is exactly what is demonstrated right here. So tip to tip, this is a wavelength, right? If we have a threshold here, right? And we want wavelengths passing through this threshold, let's say per second. A shorter wavelength is going to have a higher frequency than a longer wavelength because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of these wavelengths passing through this red threshold opposed to this longer wavelength, right? So shorter wavelengths have a higher frequency. It's kind of inverse, right, when you think about it. Important symbols to know for these equations that I'm going to be going over are, so this is a sign for wavelength. So like I said, that's tip to tip. This is a sign for frequency, so number of waves that pass by a point per unit time. And then this stands for the speed of light. So this is 300 million meters per second, right? And so meters is usually going to be the unit that we're using. We're also going to be using nanometers, but usually we're going to have to convert one another. I did kind of demonstrate it here. Shorter wavelength, higher frequency, longer wavelength, lower frequency, right? And then, like I said, this is demonstrated through this formula right here. So the speed of light, the speed of these wavelengths, for example, or speed of light, electromagnetic radiation, whatever, is demonstrated through wavelength times frequency. Okay. Visible light, not so important to know because I didn't really mention anything with visible light is between, but it's important to know that visible light is between 400 nanometers to 700 nanometers in the sense of a photoelectric effect. Red light has a very low frequency, so it's not going to be enough to necessarily knock electrons out of a metal surface, but blue light, for example, has a much higher frequency, so they are able to knock electrons out, right? This is what the photoelectric effect looks like visually. Okay, so high frequency waves are going to come in on this metal surface. These are going to be electrons, and they're going to knock the electrons out of the metal surface, right? Because these high frequency waves have photons, right? And they act like particles. Okay, so photons equal particles of light. And so this is going to be the equation if you wanted to find the energy of a photon. Okay, why would we want to know the energy of a photon? Well, if we wanted to know if this has enough energy to knock an electron out, right? Does it have a high frequency, high enough energy? Or sorry, not high enough frequency, just high enough energy to knock an electron off of this metal surface, right? We do this by Planck's constant times the frequency of a photon. Okay, so Planck's constant is a constant, so it's always going to be 6.626 times 10 to the negative 34 joules per second. It's a constant. It's always going to be that number, okay? And then you would multiply that by the frequency, and then usually you would have to find the frequency, which we will go into practice problems in a second. Okay, so for example, super simple. If we just wanted to find the energy of a photon, right? Does this have enough energy to knock a electron out of place? The frequency is given. Boom, right there. Frequency of the photon is 6.0 times 10 to the 14th seconds, right? Find the energy of the photon. So we have Planck's constant. We already know what that is. So all we have to do is multiply Planck's constant and the frequency. Okay, and what do you get? Is the energy of the photon. So the energy of the photon is 3.9756. Sure, we could have rounded that. Times 10 to the negative 19th joules, okay? So super simple. That was we were literally just following this equation right here, okay? Practice question number 2. We're going to use both of these equations. The equation, did I draw it up here? I guess not. Right here, yeah, this equation right here, right? Okay, so we're going to use both of these equations to find energy and to find the speed. So because this is in meters, we want to convert this to meters. So I didn't even read the question, I'm sorry. So light with a wavelength of 450 nanometers shines on a metal surface. Find the energy of one photon. Okay, so because this is in meters, we want to convert this to meters to find the energy, because that's going to help us find the frequency, and that's going to help us find the energy. So step one, what is 450 nanometers to meters? Okay, so what is 1 meters equal to in nanometers? 1 meter is equal to 1 times 10 to the 9th nanometers, okay? So if you watch my dimensional analysis video, you know how this works. You would put the given, sometimes I like to write it over 1. I didn't in this scenario, but sometimes you can, or you can't always if you want. So it'd be 415 nanometers, okay? 1 times negative, sorry. It'd be 450 nanometers times 1, so that's just 1. And then we divide that 1 times 10 to the 9th nanometers. Nanometers cancel each other out, so we're left with meters because this is in meters. That's what we're trying to solve for. And if we multiply that, if we divide that, this is our answer: 4.5 times 10 to the negative 7th, or 0.000000045. Okay, so answer is 4.5 times 10 to the negative 7th. So that is those are our meters, right? So now we have to find the frequency. And in order to find the frequency, so we have the wavelength right here. We have the wavelength right here. So now we're just going to solve for the frequency. Okay. So we have our constant. Okay. This is our constant, the speed of light. Constant right here. We're just going to divide our wavelength in meters to find the frequency. Okay. Super simple. We just have to work backwards a little bit, right? So if we divide 3.0 times 10 to the 8th meters per second, we divide that by 4.5 times 10 to the negative 7th, and we can get our frequency. And our frequency should be 6.67 times 10 to the 14th. Boom, so now we have our frequency. So now we can, honestly, we can ignore this equation. We already did this, okay? So the question is, we're looking for the energy. So what equation solves for the energy? This one right here. Now we have the frequency, and we already have Planck's constant. So we can just solve it, right? It's super simple now. Okay, so H times V, Planck's constant times frequency equals energy. And we should have got, 4.42 times 10 to the negative 19th joules. Okay, so joules is our unit that we're using. That is our answer. That is a practice problem using both of these equations. You kind of have to work backwards in some ways. But yeah. Okay, practice question number 3. Using the same formulas again. Practice question number 3. A photon has an energy of 3.20 times 10 to the negative 19th joules. Find the wavelength in nanometers. This is fantastic because they already gave us our energy. Okay, so now we just have to find the wavelength. So immediately, I know I can go to the first equation, this one right here, and I can just divide this by Planck's constant. So this is our energy. Divide this by Planck's constant to get our frequency, right? Because that's what we're going to need to find our, eventually our nanometers. So if we divide that to find the frequency, boom, our frequency is 4.82 times 10 to the 14th. Step 2, find the meters, okay? So we have to find our wavelength, okay? So this is going to be our wavelength in meters. Okay, so using this equation, because we have our frequency, we have the speed of light, and we're solving for the wavelength in meters, we just divide the speed of light divided by the frequency. Boom. That is our wavelength in meters. Okay, 6.22 times 10 to the negative 7th in meters. Now that we have all of that information, now we go back to dimensional analysis, which I made a video on previously. Now we're just converting meters to nanometers. We want to make sure our units cancel out. So this is our wavelength. So 6.22 times 10 to the negative 7th in meters. So how many meters goes into 1 nanometer, or what is 1 nanometer equal to? Or what is 1 meter equal to in nanometers? It's 1 times 10 to the 9th nanometers. Meters are going to cancel each other out because we're solving for nanometers anyways. Boom. So now we just multiply 6.22 times 10 to the negative 7th times 1 times 10 to the 9th. And what do we end up with? 622 nanometers. So that is the wavelength in nanometers of a photon that has the energy of 3.20 times 10 to the negative 19 joules. Okay. These formulas, once it clicks, it's super easy to understand. The constants are honestly super easy to understand. Most times anyways, you'll have a formula sheet or an equation sheet or a constant sheet. So you don't even really need to remember all the numbers. You just need to remember how to solve them. Okay. So I hope I explained the conceptualness of the wavelength in a decent way, and I also hope that I was able to explain the equations and the math pretty decently. But yeah, hope you guys enjoyed.